So today I'd like to spend the first 15-20 minutes wrapping up our discussion of force closure. And then we're going to start a new topic, namely the description of rigid body motions, in particular rotations. Okay? So let's go back and review what we know about form and force closure. Okay, so let's consider the case where we have 4 frictionless point contacts. Oops, put it here. Okay, so we have 4 frictionless point contacts. Okay. And we did this a number of times, so I'm not going to go through all the derivations. But we know that for this case, we can determine force closure by examining a system of the form AX equals B. Okay. So for this particular problem, we have force, actually because these contacts are frictionless, it's in fact here a form closure. Okay, so we have force closure if the following condition is satisfied. There exists some solution X. Okay, that's non-negative. Okay, that satisfies AX equals B. Okay, for every possible B. Okay, all right. So in this case, for example, A is going to be 3 by 4. Okay, so we're going to have A3, A4. Okay, so it's going to be a 3 by 4 matrix. So each column is a 3-dimensional vector. Okay, and B is a single 3-dimensional vector. Okay, so we established that this is a condition for force or form closure. Okay. All right, so I gave you a geometric argument, okay, on how to determine this, whether this is true or not. Okay, so what we can do is we can visualize, okay, the columns of this matrix A. Okay, so let's draw the columns. So let's say this is, let me just draw it. Okay, so let's say this is A1, A2, A3, A4. Okay, and what we do is we now draw the tetrahedron. Okay, so you have to sort of imagine this is it's a volume, it's a tetrahedron. Okay, so another way to characterize this condition geometrically is to ask the question, is the origin in the interior of this 3-dimensional tetrahedron? Okay, if we want to say that a little bit more precisely, Okay, we can ask, does there exist? Okay, so let's state it in form of a statement. So there exists some, okay, three-dimensional open ball, okay, with its center at the origin, centered at 0, okay, such that this open ball is in the interior of the tetrahedron. That lies in interior of tetrahedron. Okay. All right, so there it is. This is admittedly a little more geometric visualization of the problem. Okay. Now, by now you've solved some examples, and you've probably figured out that it's not so easy, right, to visualize these tetrahedra specifically to determine whether the origin lies in the interior or not. Okay, so it'd be nice if we had a better method. Okay. So before we discuss the better method, let's look again at this time the friction case. Okay, so we have 2-point contacts with friction. Okay, so I drew this picture for you. So we have a contact here, contact there, and we have a friction cone over here. Okay. Here are the friction cones. Okay. And we saw that for this particular problem, okay, determining force closure, now force closure this time, not form closure, because these are point contacts with friction. So if we don't apply a strong enough force, this object could slip out. Okay. Okay. So for that particular problem, okay, determining force closure is what? It's really exactly the same as this, right? Okay, so force closure this time is essentially the same condition as before. Okay, and for our example, okay, for the example that I showed you in class, we saw that A looked the following form. So let me see if I can recall from memory here. It's 1 mu minus mu r, 1 minus mu r minus 1 mu r minus 1 minus mu r. Okay? So, so you can imagine drawing these points, okay? And seeing if the origin is inside the tetrahedron defined by these points, okay? Not easy, right? Okay, so it'd be nice if we had a better method, sort of a computational method. And fortunately, there is a method. Okay. So a sort of a computational algorithm or a method for determining force closure would be nice. Okay. Okay, so let me show you the method. In fact, it's rather intuitive. And I think the best way to show it is through an example. Okay, all right, so this example is useful at a number of levels. All right, so I'm going to draw 3 contacts this time. So here's a contact here right at the corner, a contact here, and a contact there. Okay, and these are going to be 3 frictionless point contacts. Frictionless point contacts. Okay. All right, so this example is useful at one level because we now have to deal with contacts at these corners. What happens? Okay, so at this corner, this contact can apply forces, normal forces, in this direction and this direction. Okay, so it's a single contact, but it can apply forces in 2 directions. Okay, so corners are a good thing. Okay, these types of corners. So, I don't know, maybe in everyday life when you grab objects, perhaps, if you find you have a tendency to grab these types of corners, maybe that's why. Okay, from a force closure perspective, it's better. Okay, and these apply the usual normal forces in that direction. Okay, so let's label these forces, say F1, F2, F3, F4. Okay, all right, and let's call this dimension here, say L3, and this dimension here, L4. Okay, so we want to determine if this is force closure or form closure in this case. So we know how to do this. Okay. So we can just write down the matrix A. Right? We've solved these kind of problems before now, so let's just get straight to it. Okay, so our matrix A for this problem is going to look like the following. 1, 0, 0, 0, 1, 0, and -1, 0, L3, 0, -1, -L4. Okay, so where did this come from? Well, let's see. This is the force and the moment corresponding to F1. Okay, so F1 applies a force in the x direction. So we have a 1, 0 here. And let's see, the kind of moment that it applies. Well, I'm going to choose the reference frame to be here. That's my reference frame. Okay. And if I calculate moments about the origin of this reference frame, then F1 generates no moment. Okay. F2 also generates no moment. Okay. So you can see that, depending on the reference frame you choose, the calculations can become a little bit easier. Okay. So we choose this reference frame. So F1 generates no moment. F2 generates no moment. F3, the force is directed in the minus x direction, so it's -1, 0. And it also generates a counterclockwise moment, which we regard as positive. And the moment, the length here is L3, so we're going to put an L3 here. Finally, F4, the force is generated in the -y direction, 0, -1, generates a clockwise moment, which we regard as negative, -L4. Okay? Okay, so now what we're going to do is we're going to now do Gaussian elimination. Okay, solve this problem. So of AX equals B. All right. Okay, so A times some x here equals some arbitrary b. Okay, so let's write it down here. 1, 0, 0, 0, 1, 0, minus 1, 0, L3, 0, minus 1, minus L4. Okay, times x1, x2, x3, x4. Okay, equals b1, b2, b3. Okay, so that's the system that we want to analyze. See if there's a solution. Okay, and I'm sure you've probably learned about Gaussian elimination in an engineering mathematics class. So if we do that, remember the strategy is to try to make the front part of the matrix as close to being the identity matrix as possible. Okay, and then just see what happens here. Okay, all right. So so it looks like we're okay with the first two columns, 1, 0, 0, 0, 1, 0. This is a problem. We'd like to try to make this 0, 0, 1 through row additions and row subtractions, right? Okay, so 1, 0, 0, 1, 0, 0. Let's make this L3 into a 1 by dividing the entire first row by L3. So you get a 1 here. And everything else stays the same in this matrix, in the first two rows. Here you have minus L4 over L3. Okay, and then we have x1, x4 equals b1, b2, and then minus, and this is b3 over L3, I believe. Okay. Okay, so the solutions don't change. I've just changed the coefficients through row addition and subtraction. Okay, so this is almost identity, but we have this minus 1 here. So what we can do is we can add row 3 to row 1, put the result in row 1 again. Okay, and that gives us 1, 0, 0, 0, 1, 0, 0, 0, 1. And this becomes minus L4 over L3, minus 1, minus L4 over L3. Okay, times x1 through x4. This equals, let's see, b1 plus b3 over L3, b2, b3 over L3. Okay, so now this system and the original system, okay, the solutions are the same. Okay, that's what Gaussian elimination is all about. Okay, so now we can ask same question of this system. Okay, is the origin in the tetrahedron formed by the columns of these four matrices? And for this, you see it's much easier, right? Because the first three columns are the x, y, and z axes. So let's draw a picture. Okay, so we have so here's column 1, here's column 2, here's column 3, and column 4. Notice that all the entries in column 4 are negative, so that means, okay, so we kind of have to, kind of hard to draw here. Okay, so here's the tetrahedron. Here are the 4 points. Okay, now it's very easy to imagine, right? If you link, connect these vertices. Oops, sorry. Something like that. Okay. All right. It's not a very. Probably could have done a better job of perspective drawing. But the point is that because last column has all entries, okay, less than 0, Okay, it's pretty clear to see that, yes, the origin is in the interior. Okay? Lies in interior of tetrahedron. Okay, so you can ask yourself, so what's the condition for forced closure for this problem? Well, you can see that when you do Gaussian elimination, and you get to this stage, you have an identity matrix here, and you have then the column left over, you want all the entries to be negative. Okay, and that will ensure that you have forced closure in this case. Okay? Okay, so that's one way to do it. All right, what if we have more than 4 columns? Okay, so what if we what if there are more than 4 columns? Okay. Okay, so to think about this problem, let's consider the simpler 2-dimensional version. Okay, so let's suppose that we managed to reduce A to the following form: 1, 0, 0, 1, minus 1, 2, minus 1, 2, and let's make this minus 2, 2, and 1, minus 2, for example. Okay? All right, so because this is a 2-dimensional problem, okay, normally we would consider this, okay, but now we add an extra column here, and we ask, is this forced closure? Okay, if we have this A matrix. Okay, so we can draw this picture again. Okay, and we have first column, second column, third column, and the fourth column. Oops, so it's like something like that. Okay, and you can see that it is going to be forced closure. Okay, because if we connect, if we connect these 4 vertices and look at the region, okay, clearly origin is in the interior. Okay, but if we just consider, okay, these 2 vectors here, okay, what's the important thing? The angle has to be greater than 180 degrees here. Okay. Okay. So now, if on the other hand we had say we had minus 2, some large number 10, and 10 minus 2, for example. Okay. Okay, you can draw this, and you can see that this is not going to work. Okay, this is not forced closure. Okay. All right, so I mean the point I'm showing you here is that even though we have, okay, so in this case, in the first case, we wanted all the entries to be minus, okay, if you have 1 column left over. if you have two columns left over, okay, you can have non-negative entries, -2, 2, for example, 1, -2, and still it can be forced closure. Okay. Okay, so for the general case, we have AX equals B. Okay. What you want to do is do Gauss elimination. Okay, if possible, try to get it down to the form where you have A is given by some I and some matrix S. Okay, is equal to, say, so we're going to do some transformation. So this is going to be B primes. Prime. Okay, so get it down to that form. Okay. And then what you want to do is you want to focus on S. Okay, focus on S. And the condition is, can I find some positive combination of the columns of S that gives me a vector in the direction in which all entries are negative? Okay, so let me try to write that down. Okay. So let's say S is equal to, okay, so does there exist, okay, some vector W, weighting vector W, okay, that's, okay, actually greater than or equal to 0, okay, such that S times W, okay, this is all negative. Okay. In other words, can we construct from the columns of S, okay, a vector all of whose entries are negative? Okay, and the way you construct this is through positive linear combinations of the columns of S. Okay, so this is the question. Okay, if yes, then we have force closure. Okay, if yes, force closure. Okay. I'm going to let you read about the details of this procedure, okay? But I hope I've given you an intuitive, okay, feel as to where this came from and why it's true.